Section 3.4 Example 4 says the table shows the altitude of a hot air balloon during its linear descent. What equation in slope-intercept form gives the balloon's altitude at any time? What do the slope and y-intercept represent? So notice we have that at 10 seconds, the hot air balloon is at 640 meters. Then at 30 seconds, it's at 590, 70, 490, and 90, it's at 440. We can choose any of these pairs of points to use to find our slope. So we might as well go ahead and use the first two. If we use 10 and 640 as x1, y1, and 30, 590 as x2, y2, we can plug this into the slope formula, y2 minus y1 over x2 minus x1, to get 590 minus 640 over 30 minus 10. Again, reminder for slope formula, make sure that your 10 and 640 stay right above each other, and your 30 and 590 stay right above each other. You can't mix the points up. The 640 and 10 could go first, and the 590 and 30 could be second, but the 590 needs to stay with the 30, the 640 needs to stay with the 10. If you subtract 590 minus 640, you get negative 50. 30 minus 10 gives you 20. If you simplify this, you get negative 5 over 2, which is the same as negative 2.5. So our slope is negative 2.5. Now we can use any of these points we want as our x1, y1 to plug into point slope form up here. Since we used 10 and 640 as x1, y1, I went ahead and changed the color to green so that it would match our color coding in point slope. So I'm going to go ahead and plug in 640 as my y1, 10 as my x1, and negative 2.5 as my slope. Now, this gives me an equation in point slope form. However, the problem asks for slope intercept. So this is the first time we're actually going to turn a point slope problem into slope intercept. To do this, we're going to get y by itself by first simplifying the right-hand side and then adding our 640 over. So to simplify the right-hand side, we're going to distribute our negative 2.5 first. When we distribute the negative 2.5 times x gives us negative 2.5x. Negative 2.5 times negative 10 gives us 25. And that does become positive because they're both negative. Now we just need to get rid of the minus 640. To get rid of minus 640, we add 640 to both sides. This leaves us with just y. Negative 640 and positive 640 are a zero pair. Equals negative 2.5x, and then 25 plus 640 gives us 665. So our final equation in slope-intercept form is y equals negative 2.5x plus 665. Now, this will be your final answer regardless of which points you choose. You can choose any 2 points to get your slope and you'll still get negative 2.5. And then no matter which one of these points you use as x1, y1, once you distribute and move everything over, it'll always equal negative 2.5x plus 665. The final part of this problem was to explain what the slope and the y-intercept represent. So the slope, negative 2.5, represents the rate of the descent of the balloon in meters per second. The y-intercept, 665, represents the initial altitude of the balloon in meters. So before the balloon started to descend at time 0, we would be up at 665 meters. The next few slides show all of this work with some added explanations written out. And then on page 198, we have you try homework number 7. Model the data in each table with a linear equation in slope-intercept form, then tell what the slope and y-intercept represent. I have had students in the past ask if there were other ways to find the y-intercept, and there are. There are ways to find it using the table. So if you come up with a clever way to just use the table, you are welcome to do that. Usually I would go over that during class. So I'll give you a hint that if you want the y-intercept, it's going to be when x equals 0. So if you can figure out a way to work backwards to get x equals 0, whatever value you get for y will be your y-intercept so that you don't have to do as much work.